Hello, this is Crossdot and Nabla, and in today's video, we're going to be covering over section 12.7 with tangent planes. And as the name of the section would suggest, this is going to be a lot like the 3D version of tangent lines of what we've learned in Calculus 1, but extended to 3D, and we'll show that application going from 3D to 2D in this video as well. But before we even start, I'd just like to say thank you so much if you've been watching all these videos, for sticking through. It's been a project that me as a high school junior has been taking upon himself for a while, and this is something I've always wanted to do, so I really appreciate you guys for watching. But besides that, let's get right into it. So we have the definition of the tangent plane. So you have an even implicitly defined function of three variables, x, y, and z, equaling k to be some surface. F is differentiable at some x naught, y naught, z naught, with the gradient not equaling 0, which means that you have a tangent vector at that point in space, right? Then the plane through P and perpendicular to the gradient is called the tangent plane to the surface at P. And remember that P is the point at which your plane is intersecting with your curve, right? It would be similar to saying in 2D that you have your tangent line intersecting your curve at that point. Say we have like some arbitrary curve like this. We have this, that's a bad tangent line, like this, right? That's what we're going to do, but we're extending it into 3D, and we'll actually show the 3D to 2D breakdown of this to really hone in on that idea of relating planes to lines, because like we mentioned in our previous videos, is that planes are just a 3D version of a line, or a line is reducing your dimensionality of a plane, right? And it's something very, very interesting that we've seen in other videos, but we're going to actually dive deep into it in this video with Desmos as well. And for our theorem, like we said earlier, since they're perpendicular or orthogonal, perpendicular is a specific type of orthogonal. In geometry, it just really means 90 degrees, but in this case, it's still useful to us. We can actually apply the dot product, again, because since the dot product of two perpendicular vectors is 0, we can dot these and have them be 0, right? We dot the gradient with our point in space, and then we get our tangent plane right here. Perfect. Example 1. Let's just do this example together. If you want to try this on your own, feel free to do so, but I'd recommend sticking through with us right here. We have example 1. Try to find the equation of the tangent plane of 8x squared plus y squared plus 8z squared equals 16 at 1, 2, root 2 over 2. All right, so looking back at our definition right here, we have this right here. So we're going to take the gradient of this, which means we need our partials. We can also say right here that you also need the partials too, so if that wasn't enough indication that you needed to take the gradient, then that should be enough for you. And let's just get right into taking the gradient with respect to x, y, and z. So we're going to get 16x, 2y, 16z. At these points, let's just plug them in. 16 times 1, 2 times 2, and then it's going to be 16 times root 2 over 2. That just becomes 8 root 2 over 2. So then we're going to get 16 for 4 root 2. No, not 4 root 2. It's going to be 8 root 2, excuse me. 8 root 2. Dotted with this right here. And one interesting thing about this is that this definition right here kind of makes sense when you think about how we did it in 2D, where we had the tangent line always being perpendicular to the actual curve at that point, right? And the same idea extends into 3D. There's a lot of trends in Calculus 3 where if it's something in 2D, it's very likely to have some similar idea or property applied to 3D as well. And that's something cool to know as well for why the formula works as is. So this is equal to 0. And we get 16x minus 1 plus 4y minus 2 plus 8 root 2 minus z minus root 2 over 2 equals 0. 16x minus 16 plus 4y minus 8 plus 8 root 2z. I know my 2's and z's look kind of similar, but I'm differentiating with the line in the middle for the z. And then we have 8 equaled 0. So you have 16x plus 4y plus 8 root 2z. 16, 8, 8, that's 32. I can divide by a common factor of 4, so I'll just do that real quick. And I got 4x plus y equals 8, not 8, no, shush. Plus 2 root 2z, it's a lot of 2's and a lot of z's right there, equals 8. And we can plug in our point real quick just to double check. So let's just do that to make sure. 4 times 1 plus 2 plus 2 root 2 times root 2 over 2. It's a lot of 2's right there. This goes away, this goes away, this becomes 2, and that becomes 8. Perfect. So we checked our math, everything looks good. However, we can also verify this on Desmos. Right here is where we have our first example. We have the point on this ellipsoid right here, and what we're looking at is this tangent plane. And this tangent plane right here, it's mapping on perfectly, right? We can get like some sort of approximation to that, and we'll actually get into that later in this section. However, one cool thing you can do is, since we know our points for x, y, and z, if you want to reduce this onto 2D, it's very simple. And I'm keeping on the 3D graph just to make our lives a little bit easier. But what we can do is get rid of this and replace it with this. Now, what I did was the point root 2 over 2 here, I plugged it into this equation right here of 8z squared to solve for our z value, because it's kind of like a level curve for this graph. And I'm basically extracting that onto here. And you can kind of see, actually, if I replace this, this maps on perfectly at z equals root 2 over 2, which is very nice for us. However, actually looking at this is important for us. No, don't extend this to 3D. Get our point. This is actually tangent here at this value, right? And that's very, very useful for us to tell, because now we know at 1, 2, 0 that it's tangent here. And this is kind of like the this is kind of the way we would reduce the dimensions for this curve. And then that's just like the way to like visualize and look at it in 3D, right? This is a 2D version. Right here is the 3D version. And you can kind of see the difference, obviously, because one's in 2D, one's in 3D. But you can kind of get the idea that a plane is a 3D extension of a line, introducing that third variable. Usually it's going to be z, right? Going back, we are going to go to example number 2. This one is going to involve the cross product, and it's like kind of like similar to other problems we've done in previous sections. So if you feel comfortable to try this one on your own, feel free to do so, and let's get right into it. So first thing I'm going to do is I'm going to take the gradient, eight y, 8z, and then I'm going to get 4x, negative 2y, 6z, and then I'm going to get 18, 16, 16, and I'm going to get 4, negative 4, negative 4, 12. And then right here, because these are going to be intersecting each other, we want a line that intersects these two. That means that the line has to be perpendicular to both of them, which means that these two curves F and G have to be perpendicular at this point. And if they're perpendicular, that's a type of it being orthogonal, right? Which means we would refer back to our cross product, right? Our cross product definition. And so at this point, you guys probably should be getting used to taking the cross product. It's not too terrible. It's a lot of work though, and I'm going to kind of skip over the laborious mathematics behind it, the arithmetic, and just focus on our end result. Because at this point in your math career, you should be okay with taking taking the cross product either with a calculator or just doing it mentally. And for me, I already have this written down anyways, so it just saves us some time. And I'm just dividing here by 8. It's a common factor they all have, because they all have a factor of 4 here, but everything's going to be multiplied by another 2, so it's going to be 8. Some cool math trickery. And here, we can just rewrite this as a parametric. That's what the question wanted us to do. And from our earlier sections, we remember how to do this. We would have to write it like this, or we have this little squiggly line, x equals 1 plus 32t, because 1 is our x value, y equals 2 minus 19t, z equals 2 minus 17t. Yeah, so looking at this right here, we have our two curves, and they're kind of interesting, right? This is the blue one is a hyperboloid of one sheet, and this is an ellipsoid for the red right here, right? One nice thing we can do is get our point 1, 2, 2 right here, and notice how they both meet at that point. That purple dot, red and blue, just came out to be as a coincidence, I guess. This green line, however, matches on perfectly. And in this case, you could say that this parametric definition of the line for 3D curves or 3D lines is technically your 3D example of a tangent line, which it really depends on if you're using one curve or multiple curves. In this case, the one curve suffices, right, for the tangent plane, but a tangent line in 3D involves the two curves. So that's another cool thing you can do. And then you also can get approximations of this as well, given like your close values. And we're going to cover that later on in this section. Perfect. Now we're going to go on to our tangent planes of a surface defined explicitly. So far what we've been working with have been implicitly defined curves where you have it in terms of x, y, and z, but now we have it in terms of x and y, right? Now what we're going to be doing is going back to our old definition, right? Where in math, when we say something's defined explicitly in 2D, we have like y equals like something mx plus b or whatever, right? However, we've been usually working with explicitly defined curves like this, b equals some ax plus cy, right? And we're going to work on a pretty cool shortcut that can help us convert from implicitly defined to explicitly defined curves, right? And we can do this. We can say that z minus f of ab equals f sub x a comma b times x minus a plus f sub y a comma b y comma b. And this is another way of getting our explicitly defined curve to be written like this. And if you think about it, this is kind of similar to how you would write your point slope form for an explicitly defined curve in 2 dimensions, where you would have it be like y minus f sub a equals f prime of a times x minus a. The only thing you're adding now is you're adding that y component as well, because it's a multivariable function. It's not just of x, it's also x and y, right? Similarly, you would have your implicitly defined function f of x, y, z equal to some z minus f of x, y. And when you take the partials of this to solve for it, you're just going to get this. f of z equaling 1, right? So in this case, your partials are always going to be equal. Your partials with respect to z are always going to equal 1 if it's implicitly defined like this. This is just how you would convert it over to an explicitly defined curve, right? And looking at this example right here, this one, I'll just walk you through the first part of how to get to the explicitly defined from it being implicitly defined. And let's get right into it, because ultimately we want to use our implicit definition because it's just going to save us time and it's going to make the problem solving a lot easier for us. So we have a tangent plane of this paraboloid right here, and we actually have the graph right here, but I'll still show it to you on Desmos because I think it's an interesting exercise to look at the 2D to 3D conversions of these tangent planes to tangent lines, right? So we have a tangent plane for z equals f of x, y. We want to find the plane tangent to the paraboloid at this point in space, right? So the first thing we want to do is we want to refer back to our idea right here. We want in terms of f of x, y, and z. So we're going to do this. We're going to do z minus f of x, y equal to 32 minus 3x squared minus 4y squared. And that's going to be my f of x, y, z, right? So what we're going to do is we're going to add everything over that is x and y. So we're going to get 3x squared plus 4y squared plus z equals 32 plus f of x, y. What we're going to do actually is, let me cut that. Oh. Cut that as well. And this is going to equal f of x, y, right? F of x, y, z now, because we actually have our third variable right here. And then what we can do is now we can take our gradient and we can get 6x, 8y, 1. See where that 1 comes in based off of this. And even if we did it the other way, it would be negative 6x multiply that by negative 1 right here, you get 6x, right? The same idea, just we're rewriting it in a way that makes our life a little bit easier, right? So looking at this now, just plug in at our point, we get 12, 8, 1, and we can rewrite it how we normally would, given our equation. So we would now dot it with the point in space where it's x minus 2, y minus 1, z minus 16 equals 0 because, again, they're perpendicular, so therefore it's going to equal 0 by the dot product. So then we're going to get 12x minus 2 plus 8y minus 1 plus z minus 16 equals 0. 12x minus 24 plus 8y minus 8 plus z minus 16 equals 0. So 24, 8, that's 32, it's 48. So 12x plus 8y plus z equals 48. And this is the tangent plane in purple right here, mapped onto this blue paraboloid right here. And to show this again, I'm going to go to Desmos real quick to show the 3D version of this and model it like that, and then show the 2D version. So now we're looking at the 3D version that we're modeling of this, right? So our green dot right here represents the point in space that we were talking about, 2, 1, 16, right? The red obviously represents the paraboloid that we're looking at, and then the blue represents our tangent plane, right? This is nice because we can now get approximations of the general, like around this point, like if we don't have like a graphing calculator or whatever on hand, we can just do this math right here and just save ourselves some time, right? However, again, what we can do, a cool trick that we can do is actually replace the value of z into these two equations right here. So it'd be 12x plus 8y plus 16 equals 48. So then you would get 12x plus 8y equals 32. You subtract the 16 right here, right? And then you would then subtract the 16 right here for this equation right here would be 3x squared plus 4y squared plus 16 equals 32. So then you would get 32 minus 16, right? And we'll get rid of this green dot right here, and we'll replace it with this gray dot. This now gives us the tangent line at this point in space, 2, 1, 0. And all we really did was just bring it down to the origin, just to show us like how this would look mathematically to us, right? And this is a really nice illustration of the idea comparing your tangent line to your tangent plane. If I just bring it back to the tangent line versus the tangent plane, you would see that if I extended this upward, it's going to map on perfectly with the tangent plane at z equals 0, right? Because all I really did was just subtract 16 to this blue equation right here to get the purple equation, right? Similarly, we can see that if we replace this with this, you would see that inside it would map on with the paraboloid at a specific value, and it would be at z equals 16, and we can just plug in z equals 16 right here to show that. And see right here where if I go to 16, if I can label it at 16, see how it's like 16.00. What we can do is we can, we go right here, we can see that as we get to 16, these curves are going to be exactly the same. And that's a very, very cool trick that you can use not only in Desmos, but under the graphing calculator to show the translations of these 2D curves to 3D and vice versa. And last but not least, this section is going to cover over approximations. If you remember, we did linear approximations, and we get to Taylor series at the end of Calc 2. We're not going to cover over Taylor series expansions for Calculus 3. It's kind of out of the scope of this video. But there are interesting videos out there that do cover that topic, and I would really recommend that because it's really interesting foray to experience for math, in my opinion, right? So it's kind of like the same idea in 2D, but we're just extending it to a third dimension. I didn't want to be reductive and say that this class is a lot of Calculus 1 repeated to 3 dimensions. But there are some things that are just like mapping on one-to-one nearly perfectly. And this is one of those topics where it's like we can directly see like the relationship between these two things, like partial derivatives. We can kind of see like the direct lineage from single variable calculus to multivariable calculus, right? And that's okay. Some of these topics are going to map on very, very similarly, right? But going back to example 4, we have to find the linear approximation of f of xy at this point, -1, 2, 1. So first off, we're going to have to find the tangent plane that is associated with this curve, right? And we have it right here. This is our definition of the linear approximation. We know this from Calculus 1. All we have to do now is just go back to this. And this is literally what we had earlier above with our definition of the tangent line, where that went. Probably deleted it. But that's what we have right here, right? And we have to find the linear approximation of the function at this point. And at this point, I feel like this is a pretty comfortable skill that you guys should have, taking the derivative of a multivariable function, taking the partial derivatives, to solve for this, right? And let's get right into it. All right, so part A, we have to take the partial of this. Let me just rewrite it as it being 5 times x squared plus y squared to -1. So then we get -5 x squared plus y squared to -2 times 2x. So then we get -10x over x squared plus y squared squared. It's the partial, but we need to take it at that value. And then for f sub y, it's the exact same thing. I'm not even joking, because the only difference is now we're differentiating with respect to y instead of x, and there's no y term in the top, so it's just going to save us some time. negative 10y x squared plus y squared. And we just have to plug in the child real quick. So we have negative 1, 2 that we're really focused on. It's going to be negative 10, negative 1. So that's going to be 10 over 25, negative 10 over 2, negative 10 times 2, negative 1 squared plus 2 squared equals negative 20 over 25. And now we get our f sub x, f sub y. So we have that for our equation. And then we have our value for f of a comma b. And then we can rewrite our approximation as this. So this is going to be 0.4 just to save us some time. X plus 1 minus 0.8, that's because 20 over 25. Y minus 2 plus 1. So that's part A done. And use the linear approximation to estimate the value of f of negative 1.05 comma 2.1. We can do that real quick. All we have to do is just plug it back into our equation. So L of let me just write it as fractions. It's just easier for my head to understand what I'm doing. It's minus so it's going to be 4 over 5 times 1 over 10 plus 1. So this is going to be minus 2 over 100 minus 4 over 50, or let's just write it as 8 over 100. 8 over 100 plus 1. So this is going to become 1 minus 10 over 100, or equal to 0.9d. And that's our approximation. Our actual value, which we can check on Desmos real quick, our actual value on Desmos would be shown as 0.9070, which is very close. Remember that the closer you get to your approximation, the more accurate your value is going to be. This is another case example of this right here. And as we see right here, they both meet at that blue dot and are really, really close to the values. And if I had the values be even closer, let's just say it was like 2 and 2. See how close that is? 0.09799. That's to the 10,000th place. That's within 1 to the negative 4 accuracy. That's really, really, really close, right? And again, these tangent planes are, again, these tangent approximations are really, really, really valuable for us to use in multivariable calculus to quickly find the answer to these types of problems. And that pretty much covers our section for this. Thank you so much for watching, and I hope you guys have a fantastic day. Thank you.